we have got two very, very similar looking systems of equations here. And what we're going to find is that the constant parts on the right of the equation are going to make all the difference as far as what the solutions look like. So we'll start by approaching the one on the left, and we're just going to go ahead and put it into an augmented matrix. So 3, -2, and 5, -12, 8, and -20. And what we can see is that the second row, actually all the way across, we can see that the second row is actually the first row times -4. So it makes it really easy to wipe some things out. So I'm going to do row 2 is going to become row 2 plus 4 of row 1. And what happens there is pretty much row 2 is just gone. Because, yeah, -12 plus 12, 8 plus 4 times -2, and -20 plus 20. And so, yeah, so we actually get this 0 row. As far as what equations mean, a 0 row means absolutely nothing. It basically means that whatever equation we had that has just been wiped out was completely redundant. And that makes sense because that equation was exactly -4 of the first equation. They're equivalent to each other. So what we really have here is just one equation. And now what we do to solve this is we introduce a parameter because generally, yeah, like this whole thing just reduces to 3x minus 2y equals 5. And that doesn't really narrow things down for us. So what we want is an easy way to generate points of this equation. So one way that we could do it is just letting one of the two letters, our variables x or y, be a parameter t. So I could say, let's let y equal t. And so then I'd have 3x minus 2t equals 5. And so 3x equals 5 plus 2t. And so x equals 5 plus 2t over 3. And so this kind of gives us a collection of points of the form 5 plus 2t over 3. And those are all the x values. And then the y values are all actually just t. So this would be a solution here. Now we could do something else. Instead of letting y equal t, something that might be a little bit nicer is just sort of noticing ahead of time that if I'm going to let y be something, it means that my goal is to solve for x. And to solve for x, I have to divide by 3. So maybe what I might notice is instead of y equals t, I maybe want a multiple of 3. So let's say 3r instead. So that way when I divide, it's just going to make things a little bit easier. Doesn't fix everything, but it's going to make my life a little easier. And so if I do it this way, then what I get is 3x minus 2 times 3r is 5. So 3x minus 6r is 5. 3x equals 6r minus 5, plus 5, sorry. And now if I divide by 3, I'm going to actually get 6r divided by 3 is 2r. And I'm going to have to divide the 5 by 3. So I'm still going to get the fraction there, but it's still a little bit nicer. And so I have my xy is 2r plus 5 over 3. And y is 3r. And just a slightly nicer representation. They both represent the exact same set of points. We could even find one of these that is not going to have any fractions in it whatsoever, which is nice. But yeah, there's many, many different ways to solve it. So that's kind of the trick, is that you might look at your friends and they have a different answer, but it's still okay. So moving on to the next one, we have a slightly different relationship here. So here we've got 3, -2, 5, and -12, 8, and 16. So we can see that at least for the coefficients in the second equation are exactly -4 times the first equation. So we are going to still try to wipe those out because that's what makes our life easier when we solve. And if we do this, I'll get the zeros. But now what happens if I'm going to do 16 plus 4 times 5, so plus 20, that gives me 36. And the second equation is telling me that 0x plus 0y equals 36. In other words, 0 equals 36. And we know that that's not true. That cannot be true. There's no x or y that'll ever make this true. So this is not possible. That means there's no solution. Very similar looking systems of equations, but very, very different results. We have no solutions versus actually infinitely many on the left, because any choice of r or any choice of t in either form will give us a solution. So as many as we want.